welcome everybody online. We are about to start. Yeah. Yeah. Perfect. So it will be ready.
Como dijimos al principio de la clase de hoy tenemos el honor de estar con la profesora Ilaria Venanzi de la Universidad de Perugia. Si os parece, cedo la palabra al profesor García Matías, que podrá dar un poco su trayectoria profesoral, su línea de investigación principales, y veréis lo entroncado que está con lo que nosotros hemos visto ya también dentro de esta materia.
Bueno, muchas gracias, Lourdes, y sobre todo por la amabilidad de traernos el aula. Bueno, yo veo muchas caras conocidas, ya me conocéis, yo soy profesor de estructura. Pasa que hoy yo hablo realmente como subdirector de investigación de esta escuela. Dentro de las muchas cosas que estamos empezando a mover a nivel de la dirección, creemos que activar la investigación es fundamental. Esta escuela, como sabéis, yo creo que está de moda. Yo creo que cuando salís de aquí, pues las empresas se dan de leche por hacerse con vosotros. Yo creo que lo estamos haciendo bastante bien, pero aparte de investigación yo creo que hay mucho por hacer. Y entre las cosas que queremos hacer es actos como el de hoy, traeros a gente pues, de la más potente del mundo que se dedica a temas de investigación y que veáis un poco qué se hace por ahí, ¿no? Entonces, bueno, para mí es un enorme placer tener a la profesora Ilaria con nosotros. Somos colegas ya desde hace unos pocos de años, compartimos un montón de cosas. Entonces, para mí tenerla aquí es un enorme placer. Bueno, yo la conozco muy bien. Hablaros de su trabajo, pues cuando conoces a alguien incluso es más difícil, ¿no? Deciros que es una persona muy reconocida a nivel mundial en el campo del mantenimiento y la monitorización estructural, entre otros muchos campos. También ha trabajado en temas de ingeniería del viento, en temas de control, pero digamos en los últimos años donde más se ha esforzado su investigación en temas de monitorización estructural. Bueno, puedo decir algunas cosas. Puedo decir que obtuvo su tesis doctoral en 2006, que es actualmente profesora titular en el Departamento de Ingeniería Civil y Ambiental de la Universidad de Perugia, en Centro Italia. No sé si tenéis pensado iros de Erasmus, pero yo creo que es un sitio espectacular en el que uno se podría hacer su Erasmus. Entonces, bueno, por ahí tenéis su contacto. Ha publicado más de 50 artículos en revistas de altísimo impacto y tiene colaboraciones con las mejores universidades del mundo. Grupos tan importantes como la Universidad de Sheffield, súper reconocida en el campo de la monitorización estructural, pero también otras universidades como Iowa State en Estados Unidos, Trinity College Dublin, bueno, y otros muchos grupos con los que colaboran. Y bueno, eso es un poco lo que os quería contar sobre Ilaria. Así que, Ilaria, cuando quieras, adelante.
Gracias. Good afternoon, everyone. Thank you for being here. And I would like, first of all, to thank Professor Lourdes for hosting me. And of course, Professor García Matías, who is a colleague of mine and with whom I've been collaborating for 7 years. So thank you for being here. As I said, we collaborated for many years, but I never had the chance to come here to Granada. So finally, I'm here and I'm very glad of this. So today I would like to talk to you about a topic of structural health monitoring of existing structures. So talking about this in this course is quite appropriate because your focus is to investigate the health state of structures, and structural health monitoring has this goal to being able to detect any damage occurring in structures. What is structural health monitoring? Let's start with the basis. Structural health monitoring is the process of using sensors, that data acquisition system and analytical techniques to assess the condition, performance, and integrity of a structure in time. So what we do in structural health monitoring is deploying sensors on a structure, which can be a bridge, which can be an historical building, or any other kind of structure or infrastructure. Sensors can be strain gauges, accelerometers, displacement transducers, thermocouples to measure temperature, and so on. And the objective is to detect possible variations in the measured signals, which can be associated to damage. So that's the goal. Which are the advantages? The advantages are being able to detect damage in the early stage, when it is not even detectable by visual inspection. Other goals and advantages are to allow preventive condition-based maintenance. So instead of performing periodic maintenance only based on time, we can perform maintenance based on condition of the structure. And this can allow us prioritization of maintenance activities, and this can allow decision making. Which are the sensors we can install on structures? We have several possibilities. We can use strain sensors, strain gauges to detect deformation. We can use accelerometers to measure accelerations and vibrations in general. We can use displacement transducers. We can use acoustic emission sensors to detect the onset of cracking, for example, in a reinforced concrete structure. We can use temperature sensors, fiber optic sensors, and so on. So depending on the goal of what we wanted to measure, we can deploy in the structure several types of sensors, even in combination. From the point of view of the distribution in time of our measurement, we can distinguish between continuous measurements, periodic measurements, and threshold-based measurements. In continuous measure, data is collected in real time, continuously. Obtain data in a continuous manner, for example, every 30 minutes, to be able to track the evolution of the state of health of the structure. If we choose periodic measurements, we can, for example, perform a weekly measurement, a monthly measurement. Is like if we had an inspection or an assessment which is made periodically. And finally, we can only activate measurement when a specific quantity exceeds a threshold. Like, for example, if we want to measure the accelerations during a seismic event, we can set a threshold and decide when to start measuring. So when a specific level of vibration is exceeded. From the point of view of the type of measurement, we can distinguish between static and dynamic measurement. Static measurements, where our goal is to record the response under stationary phenomena, under very low varying phenomenon, like, for example, due to, let's say, creep or other low velocity, low speed phenomena. Or we can have dynamic measurements when we want to record quickly varying variations. For example, under acceleration in a bridge under traffic loading, vibrations induced by earthquake, so on. To perform structural health monitoring, very often we use continuous dynamic measurements. So we used to record vibrations in time by using sensors which allow us to track very quick variations in time. And we, most of the times, use what is called operational model analysis. This operational model analysis is a technique which is used to identify the dynamic properties of a structure. Do you know what are these dynamic properties, model properties of a structure? You probably may not know this. So just to let you understand, I can tell you that the structure vibrates by following vibration modes, its own vibration modes. So the vibration of a structure can be seen as a superimposition of its vibration modes. Okay, so recognizing these natural vibration modes of the structure allows us to understand which is the behavior. And if these modal properties, these dynamic properties, these mode shapes of vibration and natural frequencies of vibrations change in time, we can say that something is happening because the structure is changing its own dynamic characteristics. So that's the goal. We want to track in time these variations of the model characteristics, of the dynamic characteristics of the structure. And this is what OMA does. Which are the characteristics of this OMA is that it is done with ambient or operational loads. So there is no need to apply loads, but we only use the ambient vibrations, the small variations the structure has due to wind, due to the occupants which are on the structure. So we measure in operational conditions without the need of functionality of the structure. That's the main advantage of operational model analysis. And the objective, as I said, is detect changes in model parameters. These changes in model parameters indicate the variation of the stiffness properties of the structure. Okay, so we can associate this model properties variation with stiffness variations that are indicative of damage. How can we do this? How do we perform this operational model analysis? Of course, it's a complicated issue, but I try to simplify this for you just to give you the idea that is behind this. So we, in operational condition, we start, oh, just looking for the pointer. Okay, we do not have it. Okay. Well, just a moment, excuse me. Ho pigiato questo. Che?
Okay.
Okay, thank you. Fine. Is this the pointer? Since I know.
The central one should be.
Should be. Okay, fine. So I was saying, we are in operational condition. We acquire data from sensors, like, for example, accelerometers, measuring accelerations. Then we compute the power spectral density matrix of the signals and perform singular value decomposition. And we are able to associate to the peaks of the singular values the natural frequencies of the structure. Then we eventually remove from this frequency trackings the effects of the temperature and the environmental factors, because one important thing is that these model properties depend on environmental factors like temperature. So temperature's variations can be confused with damage in structures. So it's necessary to remove this from the signals, from the frequency tracking, let's say. So we do this, and then we are able to obtain what are called control charts. These control charts represent the variation of proper statistical distances from the normal values. So we compute a specific statistical distance, for example, the Hotelling distance, that gives us a measure of the distance between what is the normal situation and the predicted, the recorded situation and the predicted one, and we can see if this data, this statistical distance at a certain point exceed a predefined threshold, and this denotes damage occurrence. So this is how operational model analysis works. Of course, it's a bit more complicated than this, but just to give you some hints. And And this approach are already in the stage of the technological transfer. Professor Garcia Macias knows this very well because he developed in collaboration with our research group softwares like the two I showed in the bottom of the slide, the MOVA-MOS, which performs the operational model analysis and structural health monitoring, and another software which is called the P3P, which was developed for the ANAS, which is the main road concessionaire in Italy, which wanted to apply operational model analysis in a large set of bridges which are currently monitored by the concessionaire. So Professor Enrica Garcia, with in collaboration with our group, developed this softwares that follow exactly the path that I just explained to you, with many other additional features I do not have time to explain right now. So we are already in this stage, and of course these techniques must be improved for specific aspects, but we are we developed a lot of tools already. Another aspect I want to put your attention to is the fact that I mentioned acceleration signals, but in structural health monitoring is very useful sometimes to combine several information of different nature. So we can combine together data of continuous monitoring from different types of sensors, but we can also integrate this information with non-destructive evaluations and with visual inspections. So all these things together provide us additional information which can be very useful. For example, as I mentioned, if we measure accelerations, it's also useful to get temperatures, because we use temperature to clean acceleration data and have a robust damage identification. And then we can merge information about strains, about displacement, to have a more robust SHM approach. Additionally, we can integrate with evaluations of material strength, like, for example, if we have a reinforced concrete structure, we can extract pores and subject them to compressive test to know which is the strength of concrete, and this allows us to have more information to integrate the continuous monitor. Finally, there are some damages, even if specifically if we want to understand what's happening locally, it may be useful to integrate continuous monitoring with a visual inspection. So starting from these premises, I'm going to present to you 4 different research experiences. The first one is an approach for damage classification, which is based on solving the inverse calibration problem using a deterministic approach. The second one uses Bayesian model updating for damage detection. Then I will present you an approach based on artificial intelligence, on machine learning. And finally, I will mention my current researches on transfer learning. I work both on bridges and historical structures, and I tried for today to focus my presentation on buildings, because I know that you are more interested on this. So I selected some applications among my recent researches, which are on historical. So let's go to the first application. Before starting, I want to tell you that we can have different goals in structural health monitoring. We may want to understand if damage is present or not, and we are in the stage of damage detection. Then we can have increasing level of complexity of the problem. So we may be interested in localizing the damage, which is the second stage of SHM. Or we can be interested in quantifying the amount of damage, which is another more complex task, and be the residual life prediction. So depending on the task, we can use different approaches. If we are only interested in damage detection, we can probably approach the problem, apply a data-driven approach to the problem. A data-driven approach to SHM relies on on measurements and uses statistical algorithms. I previously showed you the control charts which use this approach, or we can use machine learning to learn patterns that distinguish healthy and damaged conditions. Otherwise, if we are interested in localization, quantification, in general, we call this classification, it's better to use model-based SHM. Model-based SHM uses analytical or numerical models. Numerical models are finite element models. Do you know what a finite element model is? It is a mathematical representation which is done with using elements like beams, like shells, to model the behavior of the structure. Okay? Do you know this? Do you have this knowledge of this? Finite element model is a numerical representation that done with a computer of the mechanical behavior of the structure. Okay, so if we use this approach via models, finite element models, we can perform damage detection by comparing what is measured from sensors and what we expect from the finite element model. Okay, we can identify different damage scenarios because we have a model, and so we can compare data with the results, the numerical results, with the goal to understand which is the damage scenario. It's not working anymore. So, if we want to use the model built an finite element model, to calibrate it, we must start from the information which are available on the structure. For example, original structural documentation, non-destructive evaluations, and structural health monitoring. SHM data allow us to calibrate, to tune the high fidelity model based on the dynamic characteristic we get from the sensors. Okay, this high fidelity model, this computer representations relates input and outputs. Inputs are damage sensitive parameters, parameters which are related to damage. For example, the elastic moduli of some parts of the structure. Okay, we can ideally divide our structure in several parts and modify the elastic moduli. Okay, if we want to reproduce a damaged condition. The output are response parameters, which are usually those we measure with sensors. So we can build this input-out relationship between elastic parameters, usually, and measured data. Then we'll see this later, reverse this problem and go from output to input. So reconstruct which are the variations of the damage sensitive parameters based on the response parameter we measure on site. This process of inverse calibration is maybe time consuming. So doing this with a high fidelity model, which is a time-consuming model, may be too challenging. So what we can do is use surrogate models. Surrogate models are mathematical relationships between inputs and outputs that we can use to substitute our high fidelity model, with the advantage that the simulations are faster, of course, and the computational cost is minimized. So when we want to go back from output, from observations we have from the records, the sensors measurement, to the input, we can use different approaches. We can use deterministic methods, Bayesian inference, which allows us to obtain an updated probabilistic distribution of the damage sensitive parameters, or we can use machine learning methods. So in my presentation, I will address these three options in three different examples. Let's start with the first. The first example is related to the Shiri Tower, which is a 41 meters high tower, civic tower, Perugia. It is partially in a building aggregate, as you can see. So it is connected to the aggregate up to the height of 17 meters, and then it continues up to 41 meters. It has a square section of about 7 meters side length. We performed ambient vibration tests on this structure. What are ambient vibration tests? Are tests in which we deploy several sensors on the structure and we measure the accelerations. Then we use the signals, as I said, to compute model properties of the structure. So here we use a set of 12 accelerometers, and we were able to detect the main natural frequencies, the first 7 natural frequencies of the structure, and the mold shapes. These are the mold shapes I was mentioning before. These are the ways of vibrating of the structure if it is left free of moving. Okay, the overall behavior of the structure is a kind of superposition of this vibration modes. Then we installed a continuous monitoring systems made of 3 accelerometers located on top. And we developed this quite simple, I want to say, methodology is still effective for our purpose, which is damage localization. Here we want to perform damage localization. So we calibrate a finite element model using the results of the ambient vibration test. Then we build a surrogate model, which is the mathematical relationship between the natural frequencies f and the mode, the model displacement component phi. The relationships with a vector u, which is a vector collecting the multipliers of the elastic moduli of the structure. So we reduce somehow this elastic modulus to relate the damage to the model parameters. This is preliminary work. Then when we get the SHM data, we track in time, perform operational model analysis and track in time the natural frequencies. We also remove temperature-related frequency fluctuation, and we fix control. If a damage is detected with this control chart, we perform the inverse calibration problem and identify which is the part of the structure which is effectively damaged. To do this, we divide the structure in macro elements in several parts. Here you can see the tower is subdivided into 4 parts. And we calibrate the finite element model with the results of the ambient vibration test, and that's the vector I was mentioning before, which collects the multiplication factor, the multiplying factor of the nominal elastic moments. With this finite element model, we are able to build the surrogate model. We can select different types of mathematical relationships for the surrogate model. Here we used a quite simple one, which is the response surface, using a response surface method. You can see that it establishes a quadratic relationship between the frequencies and mode shapes and this damage-dependent parameters vector. Then we want to solve the inverse problem and understand which are the multipliers that changed in time. To do this, we solve an optimization problem. The vector u is bounded between 0 and 1. For physical reasons, we cannot have a value greater than the nominal value. Then we minimize this objective function j, which is in a combination of a term which is related to the difference between experimental and numerical mode shapes, and another term which is related to the difference between experimental natural frequencies, those that we get from the data, and the numerical ones, those that we get from the numerical model, from the surrogate model, by changing this, the multipliers. Okay, so at the end, to prove this approach, we simulated using the finite element model 2 different scenarios, one with damage in here at the contact between the tower and the building aggregate, and another one in the macro element 3 at an intermediate height. By using, so we simulated with the numerical model the frequency decays, the variations of frequency that you can see there, and by using the optimization approach, we were able to detect the locations of the building where down. For example, here in the Manchester scenario 2, you can see that these multipliers are much lower than the others in correspondence of the third macro element. The different ones represent different combinations of the weighting factors in the optimization, the objective function. But then we also had the possibility to test the methodology with a real earthquake, which occurred with an epicenter 100 kilometers far from Perugia. We had real frequency shifts due to that earthquake, and we applied this methodology. In this case, we saw that the part of the building in connection to the aggregate was the one which was much damaged. And then we were able to check this result with the results of visual inspections and with the results of nonlinear dynamic analysis we performed on the structure by using the same accelerogram that was recorded during the seismic event. So this is the first application, quite, let's say, simple in its approach, uses a deterministic method. Now let's switch to the second one, which using Bayesian model updating. Here the case study is the Consoli Palace in Gubbio, which is a medieval palace, as you can see, made of 3 main parts, a central body, a loggia, and a bell tower. This building was equipped with a set of sensors for the continuous monitoring and was subjected to an ambient vibration test with an additional number of sensors in 2021. Here are the results, once again, of the model identification. So you can see the natural frequencies and the mode shapes of the structure. And here is the outline of the methodology. As you can see on the top, there is an offline phase, and at the bottom, you can see an online phase. In the offline phase, what we do is to use the results of ambient vibration test to calibrate a finite element structure. Then, using the finite element model, we select some possible damage scenarios. Some of them are identified by expert judgment, engineering judgment. For example, we can say that there are some parts of the facade that can overturn, and so we identify them as a possible location of damage. And in some cases, we performed, like here, we performed nonlinear dynamic analysis, nonlinear pushover analysis, nonlinear static analysis, to identify the possible location of cracks due to a seismic event. So we defined a set of possible damage scenarios. Using the finite element model and modifying the elastic parameters, the elastic modulus in correspondence of the damaged parts, we were able to build a surrogate model. This time it is a trivial kind of relationship, and here you can see the quite good fit between predicted value of the surrogate model and the finite element model estimates. Then, what's new here is, with respect to the previous approach, that we use a Bayesian model updating approach. This uses a quite well-known relationship in engineering, which is the Bayes relation. This one, it relates the probability distribution of the uncertain parameters, in this case the elastic moduli, to the measured quantities, okay, to the quantities measured by sensors. These are the posterior distributions. So what the probability distributions updated by knowing by after observations, after measuring data, for example, acceleration. Here is the likelihood function, which expresses how confident we are to have the value of the uncertain parameter given the data, and then we have a prior distribution, which is our first guess about the elastic properties. By solving this equation continuously in time, we can update the probability distribution. On top, you can see with the acquisition of new data how the probability distribution of the damage parameter shift from the blue to the red, okay? Because we got new observations that change the posterior distribution with respect to the prior. Then I go quickly on this because of time. We merge the results of the Bayesian model updating with the results we get from visual inspections and with crack measurements. In the building, we also have displacement transducers, so we are able to see if there are some increase in crack width. So there is an increase in crack opening. By combining these three indexes with the 2 out of 3 voter criterion, we can say the higher confidence that damage occurred. We test this with a seismic event which occurred in 2021 with epicenter in Ingeniería. Here you can see some frequency shifts, and you can see the results of the model updating. We identified 4 types of damages which were probably more likely to occur, and we checked on site with the visual inspection and by looking at the results of crack measurements that these were indeed the damage occurred. So applying this procedure, we were able to track time with the new acquisition from sensor the variation of the stiffness, okay, in the damaged areas. In the undamaged area, what happens is that if the Bayesian model updating and we neglect the results of visual inspection, for example, we can have some false alarms. Here you can see the decrease in the stiffness coefficient that is corrected if we integrate the results of visual inspection. So this is an approach using data fusion, visual inspections, crack opening, and Bayesian model updating to assess and localize the damage. Let's go to the third approach because time is passing quickly. In this case, I want to show you an application of machine learning, artificial intelligence in this context. Machine learning is starting being very much used in this context, as in most of the engineering fields in the last couple of decades, because it has a lot of advantages. It can allow us managing large and complex data sets It allows us to merge data from a lot of sensors, also of different nature. We can have different types of sensors that we can merge, and information in general that we can merge to obtain to pursue our task. Then it allows us to go beyond the damage detection. If we assign to the data set labels, that means we say it's damage or not, this is the damage, this is another type of damage, we are able to perform also localization, quantification, and get additional information from it. And then this model can be updated in time, are adaptive, can be improved, can improve themselves as more information become available. Which are the main uses of machine learning in SHM? We have many uses of machine learning corresponding to the main open research fields. We may use machine learning for anomaly detection and classification, but we also use machine learning for automated inspection, that is recognizing the defects by looking at the pictures of the defects. This is a very widespread application. And we can use information, visual information, for building numerical models. Then we can use it for predictive risk analysis and decision making. And we can exploit machine learning also to put together data from a large number of structures to infer the health state in a network scale context. I will briefly talk about this later on. First, let's distinguish what is unsupervised and supervised machine learning. Unsupervised is when we do not need the labels. So path covered without requiring label data. For example, the classical example is that I will do this later. Just let me introduce this. We have the supervised approach when we need labels. For example, we need to say to the algorithm, this image is a cat, this image is a dog, and the algorithm, when I give you him additional images, can distinguish between the two. But this is because I gave him the labels. This is a cat, this is a dog. Okay, so unsupervised and supervised. For damage detection, it's sufficient to use unsupervised learning, because when the behavior deviates from the normal condition, we can say that the damage occurred. For classification, that is localization, quantification, it's more useful to have label data, okay, because we can distinguish between different classes. For example, I can say this type of damage occurred or this other type of damage occurred. Regardless of which type of approach we use, this is how a machine learning algorithm works. We provide the algorithm data obtained from SHM, from sensor. We use this data to train the algorithm by giving him proper features. Then we build this predictive model using the machine learning algorithm. So that when new vibration data is acquired, the algorithm can predict which are the labels associated to it. So there is damage or not, and eventually which kind of damage. This depending on the type of information we give in input. So we need some data. We need to divide our data set in a training part for training, a part for validation, which checks somehow the performance of the algorithm, and then some data for testing, for checking the performance of the algorithm. A very important role is played by the quantities we use to train the algorithm and to infer the results. These are called features. Features transform raw sensor data into meaningful representations that can distinguish between normal and abnormal behavior. So this is a very important part. So depending on the task and depending on the type of data we have, we can use different features. Here are some examples. For example, if you want to use, if we have temperatures, we can use some statistical quantities to train the algorithm. If we have, for example, acceleration time histories, we can use square peak variance. We can use also quantities in the frequency domain, like dominant frequency, natural frequencies, mode shapes, and so on. It depends on the type of damage. If we have images to the data, we can use different features. The simplest is the RGB, the colors associated to each pixel of the image. So this is very important. And when we have time history, we must divide the time history into several windows and build kind of matrix like this one. We have a set of features for each time window. And this is the format in which we give that we give to the algorithm. Very quickly, these are two types of neural networks, but I think that the time is quite going on, so I missed this. I skipped this one. Here is an application of machine learning for a specific problem of damage anomaly detection in the Consoli Palace, the one I previously showed you. In this application, we wanted to take into account, in addition to data from accelerometers, also temperature data. Okay, to improve the capability, the anomaly detection capability of the algorithm. So what did we do? We used data from several sensors. We performed the singular value decomposition of the power spectral density to get singular values, and we concatenated the singular values with the outside and inside the temperature, and we trained a specific type of machine learning algorithm, which is the convolutional autoencoder. These autoencoders reconstruct the input so that we can decide if the reconstruct, when we give new information to the algorithm, we can decide if this new piece of information is related to damage condition or not by looking at the reconstruct output matrix. Okay, this is the training and testing period. This is architecture of the machine learning. We used a loss function, which is the sum of different contributions related to the singular value reconstruction, to the temperature, and another one for feature consistency. And then I go quite here, I cannot go into details. We used some adjustments to be able to better account for temperature compensation. And we had quite good results that without all these adjustments, we weren't able to get. These are the results in terms of damage detection. You see the red significantly deviate, the red point significantly deviate from the previous ones. The different graphs represent different features we used to check the damage occurred. Just to give you a hint, very, very quick, few minutes, on what is transfer learning, the last application I want to show. So transfer learning is a process of transferring information from one structure to another. In real practice, in real world applications, we have some limitations to the application of machine learning. In particular, we need a large amount of training data, and in practice, we very often do not have damage data, because in real structures, hopefully they are not so damaged. So we cannot have real data. So to overcome these problems, the idea is to transfer the information we get from one structure, which has been monitored, for example, for a longer time, or for which we have more information in general, transfer to another structure, which is somehow similar, shares similar characteristics. One approach to transfer learning is what is called domain adaptation. In this case, we have the source and the target structure. We have two different structures. And we train a classifier on the source structure, the one for which we have more information. Here we have, for example, damaged data, undamaged and damaged data. If we want to use the same classifier for another structure, we can't because we have generalization issues. So the idea is to get a shared latent space in which the classifier works well for both source and target data. So the idea is to merge the domains, the latent space, to get to have a classifier which works for both. We have different approaches, and we mainly applied these approaches to bridge, where we saw that it works quite well. But we are thinking also about using this approach for different types of structures, in particular for mesory structures. Here you can see smart bricks, which have been developed by my colleagues at the University of Perugia, Antonella D'Alessandro, Professor Filippo Bertini. This is a type of smart material, smart masonry, which is dealt with the steel fibers. These steel fibers provide the material the capability of being sensitive to strain. Okay, so if a load is applied on the brick, see here, we can detect a variation in the current intensity we have from one electrode to the other, and so this is related to damage. So the idea here is to apply transfer learning between simple structures and more complex structures we may have in reality. So we train a machine learning classifier with an archetypal model, a simple structure, and then we use the information from the smart bricks to apply to a more complex structure like the one you see on the right. As a first attempt, we use domain adversarial neural networks that exploit an adversarial training to merge the two domains and allow the classifier to work well also in the target domain. I do not have, time to go into further details. It's a nice approach that seems quite promising. We used it also for bridges. And here you see the panels equipped with smart bricks for those light poles. We tried to simulate an earthquake. So we applied to this wall a cyclic in-plane loading up to different values of load. We got the strain. This is done numerically for the time being. We get different strains in correspondence of the smart bricks, and we train this domain adversarial neural network with the final goal of identifying the type of damage that can be bending, compression, shear in a real structure. This is an ongoing research, and so that's it. I conclude saying that SHM has the goal to assess the integrity of the structure. This requires solving the inverse problem, and I show you different approaches for doing this. And then we ended with the concept, just a hint on what is transfer learning, which seems quite promising in the field of health monitoring that allows to merge the fields of machine learning and structural health. I just want to thank the group. This is not the whole group, but those are the people who contributed to the researches I showed you. And I want to mention once again, Enrique, here he was much younger, probably. And Boris, of course, he was involved in most of these activities, and he was one of the main contributors to what I showed you. So I thank you for your attention. I'm sorry for being a bit late, and any question is welcome.
Chicos, muchísimas gracias. Vamos a un poquito más de tiempo, así que os dejo que cogéis. Yo, bueno, por lo menos espero que, es cierto que el contenido matemático en algunas partes quizá ha parecido un poco duro, pero bueno, es que ha traído a una persona que está al top en este campo, entonces que no voy a traer otra cosa, ¿no? Primero espero que por lo menos una visión de por dónde andan los tiros sí que os haya quedado. Y bueno, sobre todo esta parte de patrimonio que muchos ingenieros civiles como yo os estamos quitando el pan y no debería ser así. Deberíamos tomar el liderazgo y echarnos a nosotros, porque realmente esto son competencias vuestras, ¿no? Entonces, bueno, yo os animo, si tenéis alguna curiosidad, que podéis escribir, y si, bueno, si no habéis copiado su correo, me podéis escribir, ¿vale? Nada, libre, muchísimas gracias por asistir.